So let's start with a brief overview of today's talk. First, I would like to talk a little bit about what are Scalable Vector Extensions, short form SVE, and some of its key architectural features from debugger's perspective. Then we'll talk a little bit about how ARM architectures has evolved from VFP to SVE and what implications that has had on debugger support. Then we'll talk what interfaces has been added in Linux and ptrace to support user mode access to SVE and debuggers. And then we'll talk about challenge of SVE, what things needed to be done, and what were the challenges of SVE enablement in LLDB, and how we are coping with those challenges. And in the last part of the presentation, I'll talk a little bit about other projects which we might be doing in next year or so, which are related to SVE and other architectural support in LLDB. So first of all, what is SVE? It is a scalable vector extension to ARM v8 architecture, and it's not an extension of Neon. Rather, it has its own set of instruction encodings, and the target is high performance computing and machine learning applications where data intensive work is required. And the first adoption of SVE was from Fujitsu, where it was selected as the architecture of choice by for post-K supercomputer. And SVE is designed as such that it utilizes and enhances the auto-vectorization capabilities of modern compilers and provides hardware support for that purpose. So now let's talk about some of the key architectural features of SVE. The most important feature from debugger point of view and otherwise as well is the fact that it is vector length agnostic, which means that it has 32 vector registers called Z registers, and those Z registers can change their size anywhere in between 1 to 8 bits to an architectural maximum of 2048 bits. And the configuration can be done as part of your SoC specification or by the Linux kernel as well. And these Z registers can pack scalar as well as floating point operations. Let's talk about some of the other features as well. It's an important feature is gather, load, and scatter store, which is basically the ability of instructions which are provided as part of SVE to load data into these vector registers from multiple non-contiguous memory locations, and then do operations on that data and then store that data to multiple non-contiguous memory locations. The addressing mode and relevant instructions are provided in the SVE instruction set to support this feature. And let's talk a little bit about the predication capabilities introduced inside of this scalable vector extensions. So the predication is the capability of a processor to run both the taken and not taken part of the branch, and then select the correct path based on the predicate value. So SVE adds 16 registers, predicate registers, which are also size varying, and they can change their size based on the size of Z registers. So for every Z register inside SVE. There is so the size of a Z register is basically if a size of a Z register is 16 bytes, then there is 1 bit for each of those bytes in a P register. So for a 16-byte Z register, there is a predicate register of 2 bytes or 16 bits. So there are 3 types of predicate registers. They are basically used interchangeably, except for the first fault register, which is our 16th predicate register, and it is used for the memory accesses which cross the page fault boundaries, and we need to speculatively tell which load inside the vector register caused that problem, and then save the state up till that point. So there are P0 to P7 registers are used for per lane predication, and P8 to P15 are used for the loop management, and FFR is, as I told you, is used for vector partitioning and software managed speculation. So this detail is sort of out of scope of what debuggers, it's not as such as relevant for debuggers, and I'm going to talk about the registers as such and not how they're used inside SVE. So let's talk a little bit about how ARM architecture has evolved and what implications this evolution has had on the support in debuggers. So we've initially with VFP we had 32 single precision registers, and then came VFP v2, and we got 16 double precision 64-bit registers. And the mapping also was available between the single precision and double precision registers. And in this case, these single precision registers became the pseudo registers, and the actual registers were double precision registers. So moving on to VFP v3, we got 32 double precision registers, or Neon, where we got 16 vector registers of 1 to 8-bit each. And the mapping here is that each smaller register is packed into the larger register, and we have now Q registers as the main register, and D registers and S registers. Both of them are now pseudo registers. So the Q registers can pack these register values and can run scalar as well as fixed point, floating point computations. So moving on to ARM v8. So with ARM v8 we got a slightly different view, because we got 2 execution states. One of them was AH32, which was like backward compatible view to ARM v7. So it is quite similar. As you can see that Q0 is the main register, and then it packs D0 and D1, and then each of D register packs S0, S1, and D1 packs S2, S3. So but with ARC64 we got a promotion, and we got 32 1 to 8-bit vector registers, and these registers mapping was different from what traditionally has been before that, like in ARM v7 and AH32. So now each of these pseudo registers, which is S register or D register in this case, maps onto the least significant, corresponding least significant bits of the corresponding V register. So S0 will map onto first 32 bits of V0, and S31 will map onto first 32 bits of V registers, V31 register. So the mapping, as you can see, has now changed, and the pseudo registers in this case are S register and D register, while the V register is the actual register which we have memory for. So now if we look at what changed with SVE, So now in this SVE, we got 32 Z registers, which had minimum size of 1 to 8 bits. And in that case, if the size is configured to be 1 to 8 bits, Z register is actually same as V register and maps onto V register, D register, or S register, similar to the one in ARC64. So first 32 bits maps to S register, first 64 to D register, and first 1 to 8 bits map onto the V register. And similarly, for every Z register, we have a corresponding V, D, and Z pseudo registers. And apart from these registers, we do have predicate registers from P0 to P15 and FFR. The first fault register. Also, we inherit FPCR and FPSR from the floating point register set of ARC64 and ARC32. So if we look here, a lot has changed. The main thing that is challenging us is the size variability, where the register size can change from 1 to 8 bits to 2048 bits. So this support has been, open source communities have been pushing support into Linux to allow the user applications to use SVE capabilities, as well as the support has been pushed into ptrace interface so that hardware can support the debuggability of SVE applications. So for SVE register data, it is a per thread register data in Linux, and every thread has its own view of Z registers, P registers, FFR, FPCR, FPSR, and corresponding GPRs, and similar to the register file that we have in ARC64. Also, there are multiple ways to access the hardware capability, if whether the SVE is available on that hardware or not. Either we can use the aux vector and figure out if hardware provides the SVE capability or not, and that is just to let the user know that this architecture and this particular OS running on it supports SVE, but that doesn't necessarily means that current thread has enabled SVE support and is using it. So for that purpose, debuggers can use ptrace interface to ask for SVE capability, which I'm going to be talking about in a bit of detail just in a bit. And then the user applications can configure SVE based on process control, PRCTL calls, and they can control the currently configured vector length, and also configure the SVE data based on whatever their requirements are. So the figure shows the SVE user header. This is the header which basically we get when we ask ptrace interface to return anti-ARM SVE red set. So let's talk a bit more about it. Yeah, sure.
On the previous page, could you clarify the Linux per thread? Is that related to core and thread in the hardware, or it's just Linux?
It's the Linux thread. So each thread has its own view of the register file. So the values that you are viewing in your current thread are different from the values which are in the other thread. And once you context switch, your data is either, this is basically governed by procedure call interface. And whatever the rules are, based on those, you either lose or save the data and then move to that. So it's the context, in the context of context switching between threads in Linux. Not per thread in hardware level. Okay, so we get a anti-ARM SVE red set data for ptrace interface. With that, we can query get red set calls or set red set calls and either configure SVE using the user SVE header, or we can read data about SVE and its payload register sets information from the ptrace interface. So similarly, there is a code dump interface as well, which is also per thread, and once a code dump is generated, there is a note that is added, which essentially lets you read the information from core file when you start debugging it using GDB or any other tool. So the more details to SVE Linux support, like signal handling, syscall handling, and other stuff, which is quite well documented in Linux kernel documentation, and you can read about it from there. So from debugger's perspective, I'm going to be talking about ptrace interface and how it is utilized to read data about SVE register set, and what are the different types of payload that is returned by the ptrace interface. So moving on. Okay, so here is a picture of the payload if we are running in non-SVE mode. So we have user FPSIMD state, which encapsulates the 32 V registers of 1 to 8 bits. So if we give a ptrace call with anti-ARM SVE flag, three outcomes can happen. First outcome is that that call fails, which essentially means that the current thread does not support SVE, and it is a simple ARC64 mode thread. So for that, we will have to use the traditional anti-FP red set call, and the anti-ARM SVE red set will be invalid for that case, and will be returned this particular struct, and the format of that data will be without the user SVE header, just the V registers followed by FPSR and FPCR. So there can be two other cases where we send the ptrace call with anti-ARM SVE flag, and we get a success, but success doesn't necessarily means that SVE is live in that particular thread. So what it means is that registers are either configured to be used or not configured to be used. So if the registers inside SVE are configured to be used, then there will be, so let me just go back a little bit and discuss this user SVE header. So the first part of the thing that we read from ptrace is this user SVE header, and it gives us very meaningful information about what follows. So there can be a set of V registers that follow, or a set of Z registers followed by P and FPSR and FFR. So for that, we need to figure out which register set data is this, and that basically is configured in these flag field of this structure. And so whenever we are reading information out of ptrace, first we read the flags and then decide whether it is a SVE thread, normal ARC64 thread, SVE thread where registers are live and we have a proper SVE payload, or it's they are not live and the payload is just a mirror of a normal FPSIMD payload. So the flag field SVPT reds FPSIMD tells us that it is just a normal FPSIMD payload, and if the flag field is returned as SVPT reds underscore SVE, then we get this kind of payload where we have user SVE header on the top, then followed by size varying Z registers, and the size can be figured out from the currently configured vector length from user SVE header. After the size is figured out, then we can calculate the size of the whole of this payload and then read it into the debugger and show the values to the user. So this is what ptrace interface has provided us. Now let's talk a little bit about challenge of SVE in LLDB. So traditionally debuggers have been used to targets which don't have size varying registers. So in this particular case, the registers have size configurable and varying size. So this means is that at the start of a debugging execution, you don't actually know which configuration is currently running. Either it is an AARC64 thread or it's an SVE thread with SVE live. It's an SVE thread with just the normal FPSIMD data. So this information needs to be figured out dynamically, and traditionally debuggers configure themselves, or the debugging thread configure itself as a single architecture and fixed length register sizes. So the first challenge is the dynamically changing registers, and based on that, the dynamically changing register descriptions. So at the start of any debugging session, debugger describes a target, and in that target there are lots of different things, including register descriptions. So for example, GDB exchanges a target description XML, and in that target description XML with remote, it has description about the register file. Similarly, in LLDB, we have register set packet, which describes all of the registers present in the current thread, and that information is exchanged once per execution, so once per process that is shared with the remote. So what happens is that we need to describe these registers so that they can change their sizes from between 128 bits to 2048 bit, and then we can also choose between the descriptions. Either these are AARC64 descriptions which have V registers, or these are SV descriptions which have Z and P registers. And also the V register has a pseudo meaning in SVE. So in case of SVE, our V register becomes pseudo register, so we need to dynamically change that as well. And in case of AARC64, the V register becomes the main register. So for that thing to happen, we need to add the support for dynamic register lengths as well as dynamic register infos, and also add the capability in LLDB to change the register capability between remote and the target dynamically. So a lot of that thing has been completed, and we have already added the dynamic register infos and dynamic register sizes, and we are moving on towards the sync between remote and target. So the other thing that is important and very a challenge to LLDB structure was that there were fixed length register classes. So the data that holds the register values was fixed length, and we could not vary the length of those that data. Now with SVE, we have added the capability to move that register length to a maximum of 2048 bits, and also the payload can also change based on the currently configured vector length. So the payload size is configured by reading the information from ptrace, and once that changes, we revert back to the normal AARC64 state or whichever state we are in. So there are lots of minute changes that are required to make this happen. So if we consider the remote and target, the problem here is that GDB has a native part where you have a native execution, and then you have the remote execution as well. So with LLDB, everything is remote and host. It's not the native portion is not there. So every time you have to rely on the RSP protocol. So the sync between the remote and host is also needed. So in case of that, we once we change the register sizes and register values on the remote size, that information has to be relayed back to the host as well, so that the register infos there can also be reconfigured to use the newly configured vector length. For that, we are considering a couple of options. So GDB is using this information is relayed back to GDB. The newly configured vector length is relayed back in the stop reply packet, which is sent as information about frequently used registers on the target stop. So whenever a thread is stopped, that information is relayed back to the host GDB, and then based on that, GDB can configure the currently configured vector length and reconfigure both host and the remote side. And in LLDB, we have dynamic size dwarf expression bytes field in the in the register info packet, and we can use this to configure the vector length and change it across. So I'm just about to finish. Yeah. So the vector length can be changed based on the dwarf expression. So this is something that we are evaluating right now, and see which one of this approach fits us best. So in the last part, I've already covered the slide. So in the last part, I'm just gonna talk about a few projects that we are doing. We are doing LLDB ARM maintainership using buildboards and trying to fix some bugs. We are doing LLDB SVE testing using QEMU, and we are looking for some other options for that. And then there is upcoming projects that we might take up in next year or so, which is tag pointer support, SVE2 and TME support. I'm not sure if how much debugger work will be there in those two projects, but the tag pointer support is required in LLDB, which we'll be doing in the future. So this is about LLDB's support, SVE support in LLDB. We have the capability to disassemble the instructions in LLDB. It was just pulled in from the LLVM disassembler, and we have done around 50 to 60% of the work in register access as well. So in the by next connect, we should have LLDB SVE support fully functional in LLDB. So that's it from me. If you have any questions, please do ask. And thank you so much.